When we speak about logistic regression, we need to give a little bit the background of the situation to understand why we have to move away from a simple linear regression, for example, and we need something different. Now, the first thing that should be clear is that logistic regression is the model you should always start with when you want to model a binary target. A binary target that is also known as a dichotomic target, a Boolean target, a dummy target, is a target that can only attain two values, is a categorical target that can only attain two values, and the two values represent two different categories. Now, we will see that the assumptions that we need in logistic regression are not the same that we have used for linear regression. Why? Because first of all, we will drop the assumption of normality of the target, because obviously if I have a categorical binary target, it cannot be normally distributed. I will also drop the idea that the mean of my target can be expressed directly with a linear predictor. We will need to introduce some function g that links the mean and the predictor. What is a binary target? A binary target is actually something very common in statistics, and many problems that can be dealt with, for example, a continuous target, can also be transformed into problems of classification in which I have a binary target. Think, for example, of a model that wants to decide if someone is admitted or not to a master degree, to a bachelor program, to a PhD, to any type of situation. So you have to decide if you want to admit or not someone. You want to verify if a possible customer can be satisfied or not. You want to grant or not a specific credit card, a mortgage. You want to estimate if someone will be tall or short. You want to see if something is heavy or light, and so on. So every time you have this dichotomic situation, and you see that if I want to consider tall or short, obviously I can also consider the height of people as a numerical continuous quantity, but I can also set a threshold and say, if you are taller than this, you are tall, if you are below, you are short, and I can transform my continuous target into binary one. So typically, we can play with whatever type of binary encoding of our categorical target, but it is somehow preferable to use with 0, 1. Typically, you assign the value 1 to the category you are most interested in and 0 to the other one. So imagine, for example, that we are in the medical sector and we are studying, for example, a given illness, a given sickness, like a heart attack. And we want to estimate what is the probability that someone develops the sickness or not. So if the person has the sickness, that will be category 1. The other category, so the person is okay, or at least without that specific sickness, that will be category 0. So you see that I have two categories, 1 and 0. The interpretation of the categories obviously will depend on the problem that we are tackling, but it's a very simple setting. Now, imagine that we start with a very simple situation in which we have one binary target and one feature. Now, the typical plot that you can expect if you create a scatter plot is something like the plot you see here in the slides. So what do you have? You have that obviously your target is binary, so can only attain two values, 0 and 1. And the feature, conversely, can be, for example, a numerical feature. So I have that for many different values of x, my y can only be 0 and 1. So this is the typical plot. I see that some points will be on 0, some points will be on 1. Why? Because y can only be 0 and 1. For example, on the x-axis, I put the blood pressure measurements for my patient. So I can have very different blood pressure measurements. So that are different values that are numerical. And then on the y-axis, I only have if the patient is sick or not, sick 1, not 0. Okay, so you see that obviously this is the type of plot that I can expect. Now, what is the problem with this type of plot? Immediately, just looking at this plot, it should be clear that linear regression, a simple linear regression, because here we just have one feature, but in the multiple linear regression case with more features, the interpretation would be the same. We cannot actually use our linear regression for many reasons that we can somehow summarize in 3 main situations. There are the assumptions, some of the assumptions of linear regression that are falling, the problem of bad fit, and also the problem of wrong representation. So let's start with the assumptions. It is clear that if I have a binary variable that can only attain value 0 and value 1, so if I have 100 observations, say that 60 observations are on value 1 and 40 are on value 0, what I have is something of this type. So obviously is an histogram of this type. Now I think that no one will essentially be surprised if I tell that this cannot be normally distributed. Okay, where do you see the bell? Where do you see the symmetry? Where do you see all the characteristics of a normally distributed random variable? When you have a binary target, so something that only attains the values 0 and 1, for example, also the concept of correlation does not make sense, because correlation is meant to measure the linear dependence between two quantities, but the two quantities need to be numerical. You cannot compute the correlation between a binary categorical target and a numerical quantity, for example. So it makes no sense to compute correlation. Or you can somehow compute correlation, as we shall see, but it's more to have some educated guess about a starting point when you want to have a forward approach in logistic regression. But that correlation should never be interpreted as a real measure of dependence, because one of the requirement of Pearson's correlation, so the typical correlation we all use, is that the two quantities you are essentially using to compute correlation are numerical and continuous. Or if they are discrete, you have many possible values, and so, okay, you can somehow use discrete quantities because you can see that as a discretization of a continuous variable. But in any case, it's important to understand that if you have just a binary variable, correlation makes no sense. And also the idea of homoscedasticity, again, makes no sense, because you